Alright, we are looking at reviewing quadrilaterals, kite, and trapezoid. This is our 6.01 asynchronous lesson for today. So by the end of class, you want to be able to classify a quadrilateral based on its properties, which is our standard. Our itinerary for today will be to review quadrilaterals, review kites, practice problems related to those, review trapezoids, and practice problems related to those, and then focus on your exit ticket for today. So remember your shape hierarchy reference slide to understand which shapes belong to which types of families, and all of these are quadrilaterals, so they all belong to that particular family of polygons. Specifically, we want to review the kite today. We recall that a kite is going to represent a four-sided figure, which is a quadrilateral, and it has two sets of adjacent congruent sides as well as one set of opposite congruent angles. So more specifically, we have all of the properties that are referenced here, and you can see that we have the two sets of congruent sides, and we have the single set of congruent angles, which are here and here. We also recall that this diagonal is bisected by the other diagonal AC. So those are two equal halves. And the diagonals are perpendicular as well. Please, please, please take note that you have right triangles created in the shape of the kite because the diagonals are perpendicular. So we notice that this angle at the top has been cut or bisected, as well as this angle at the bottom. So if you look at that diagram, you can see it creates two different right triangles ultimately. One right triangle has degrees 41 and 49. And the other right triangle, if I were to draw it this way, has degrees 63 and 27. Now that's just the angles that they've provided, but I'm just kind of showing you that those right triangles are created because of those diagonals being perpendicular. So let's go ahead and take a look at an example where we can maybe reference using one of those right triangles. And I will remind you that the triangle sum theorem can also be used as well. So if you look at your answer key on your slides today, you'll probably see that being shown. I'm hoping that in the video I'll show you another approach that you could potentially use as well to help you solve your problems today. So we are looking for the measure of ABD, the angle ABD. So ABD, of course, if I get really close to my diagram, is going to be right here. How do I know that? Because it goes from A to B to D, that angle. Now, I want to remind you that the diagonals are perpendicular. So because this diagonal and the other diagonal are perpendicular, you have a right angle right there. And they've told us that this angle over here is 78 degrees. 78 degrees. That's the angle DAE. So I'm going to go ahead now and remind you that I'm highlighting in green that this angle right here, the entire angle located at that vertex, has been bisected. So what does that mean? Well, that means that this angle is also 78 degrees. Our task is to find this angle right here. So what I'm going to now do is show you how you have a right triangle right here. And I'm kind of highlighting that triangle now. And so I'm going to draw that triangle out for you. And I'm just going to place it right here. And actually, I'll go ahead and draw the whole thing, and then I'll be able to create it. There we go. So recall that this is where E is located, and there's a 90-degree angle there. We know that this is 78 degrees. That's this angle that I'm referring to right here. How do I know it's 78? Because the whole angle was bisected, and these two angles are congruent to each other. Now, when you have a right triangle, you're missing this angle right here. There are two ways to solve for this missing angle. In my view, the easiest way to find the missing angle is to simply take 90 degrees and subtract 78 degrees. That's going to get you 12 degrees, and that is the value you are looking for in the triangle. The other thing you have to remember is that the sum of all of the angles in the right triangle, or in a triangle, equals 180. If you were to take 180 and you were to subtract the sum of, in this case, 90 and 78, you would get 180 minus 168, and this would also equal 12 degrees. So you can use either approach to finding the missing angle value located at that spot. I highly recommend that you refer to this for your exit ticket question. There is a specific question where this could be very helpful. So let's take a look at another case of this, another example. We identify over here that we have perpendicular diagonals. So what does that tell me? It says that I have some right triangles here, and right away my eyes are drawn to where I'm looking for my angle. I'm looking for this angle here. Notice that I can observe this right triangle right here like I did in the previous example. So I'm going to construct my triangle here. Here's my right triangle. This is where P is located. This is J, and this is K. Now, do you notice how they've told us the entire angle at the top is 48? Remember, and I'm going to highlight it in green, this diagonal is bisecting this entire angle. That means it cuts it into two equal halves. So that means this angle here is 24 and this angle here is 24. So I know this angle is 24 degrees, and I am looking for this angle right here. So what can I do? Well, I could just take 90 and subtract 24 from that, and that's going to get me 66 degrees. Or what I also could do is take 180 and subtract the sum of 90 and 24. And so that gets me 180 minus 114, and that also gets me 66 degrees. So either way, I get the correct answer in either approach. That's how I find the missing angle measure for JKP. JKP is this angle right here. Okay, so the measure is going to be 66 degrees. Now let's take a look at the trapezoid review. Recall that for a trapezoid, these are the legs of the trapezoid, and the bases are the sides that are parallel to each other, right? So when it says one set of parallel sides, that's going to be the bases. The bases are going to be the parallel lengths. We also can identify as well the base angles BC and the base angles of A and D as well. And so this was a slide that we covered that day when we talked about trapezoids. So we know that these are supplementary angles, and as are these, because they're between two parallel lines. But these are not supplementary because they are not between parallel lines. So reminder that if you're going to use Desmos as a tool to help you create the visualization for this trapezoid, or the one you have on your exit ticket, just remember to put the first set of ordered pairs at the end as well. And reminder, in the YouTube channel for our geometry team, we actually have a video or two in there that demonstrates how to do this in case you have forgotten. So I already have the image plotted here on the right, and we want to identify what the bases of the trapezoid actually are. Now, I want to remind you that you can, in fact, use your slope formula if you would like to use the slope formula in this problem. Why would you want to do that? Well, in order to identify the bases of the trapezoid, you need to identify the sides that are parallel. Now, it seems kind of obvious here where parallel sides are at, because they're the sides that do not intersect. So if I were to label the figure's vertices A, B, C, and D, it's very clear that BC is parallel to AD. And so those are going to be the bases, right? So the two bases are BC and AD. However, don't forget that you can also check the slope using the slope formula. And I highly recommend that if you doubt whether two lines are parallel, to double check the slope if in fact that's the case. So if you have the visualization in front of you like this, as we recommend that you do, then what you can actually look at is the rise and the run, rise over the run. So for example, this goes up by 4 and it goes over by 6. So that line AB, slope of AB, is actually 4 over 6, or 2/3. However, the other line on the other side, which is one of the legs, this is another leg as well, it goes down 4 and then it goes to the right by 5. So the slope of the other line is the slope of line CD. It goes down 4 and to the right by 5. And these two slopes are not the same. If they're not the same, the lines are not parallel. So AB is not parallel to CD, and that confirms that they cannot be the bases of that trapezoid. So that's one way to tell using rise over run, or you can use your slope formula as well if you wish to do that. The final example here, and I did forget to mention, I would refer to this as an example for your exit ticket question. I highly recommend that you try to use the Desmos graphing calculator because it can make for a quicker work on that problem. The final problem that we're going to address is related to the trapezoid midsegment, which is really just the average of the bases of the figure that is a trapezoid here. So I'm going to give you your example. Here is a trapezoid, and the midsegment is half the sum of the bases. You can think of that as the average of the bases. So here's base 1, here's base 2. So we know that EF is the midsegment. And how do we know that it's the midsegment of the trapezoid? Because its endpoints are the midpoints of the sides of the trapezoid, or the legs of the trapezoid. That's how we know. So EF is very easy to calculate because we just need to take our two base lengths, add them together, and we're going to divide that sum by 2. So our mid-segment length for EF is going to be 6 in this case. Again, I highly recommend you refer back to this slide for your exit ticket for today. It can be very helpful in reminding you of what you need to do. Speaking of the exit ticket, here it is right here. So if you look at the first question, again, I highly recommend using Desmos. And remember that when you talk about parallel lines, right, parallel lines have the same slope, the same exact slope. So I'm really kind of giving you tips there on identify the lines that have the same slope. Refer to the video on how to plot points using Desmos if you need to do that. That can be very, very helpful for you. On the second question to the right with the kite, again, I highly recommend you refer back to our example here. This is a great example to refer to. You have two different approaches that we talked about for how to locate the angle missing. You have a very similar setup to this as well, so please refer back to this particular slide or in the part of the video that I talked about it to help you on that question. You are looking for JMP, which is clearly labeled as this angle right here. Lastly, of course, I would refer back to the mid-segment of a trapezoid problem to help you on the final question. You are tasked with finding the mid-segment length of the trapezoid given the lengths of the bases. So that'll be a very quick and easy total for you to find, as long as you again refer back to this formula and this example for that. And so that's going to represent your lesson for 6.01 today for your asynchronous lesson.